So let's continue with the second lecture. So just before that, let me notice that in the theorem of types, F1 and F2 should not be degenerate. If they are degenerate, there is no reason why the limit of this quotient should exist. Okay? It could be 0 or infinity, or it could be anything. Okay? Gn should also not be degenerate. Also in the theorem, by the way I state the theorem, x0 should be equal to 0. Okay? So the process, the self-similar process, should start from 0. But there are more general versions of that. And I think I said something wrong also in the second example, the extremal process. The scaling property of the extremal process is of this form. Okay? So just extremal processes are alpha self-similar. Okay? Just 3 remarks that I observe now during the break. Okay? Well, there are many other results connecting self-similar processes via scaling limits. And there is one that I want to point out that is more recent, that was proved by Benedict As and Mirmont, and later generalized by Bertoine and Igor Korchemsky. Sorry, Igor, I think it's not the right spelling. Korchemsky. Okay. And this connects scaling limits with self-similar Markov processes. Okay. Let me just state the theorem of Haas and Mirmont. I will not state the result by Bertoine and Korchemsky, but it's very similar. And notice here that by self-similar Markov process, we will mean self-similar processes having the strong Markov property. Is everybody familiar with the strong Markov property? Yeah? Everybody knows what is a strong Markov process. Okay? If not, just let me know. Okay. So what is the theorem of Benedict and Gregory saying is that if we take xk for k positive be a Markov chain, a discrete Markov chain taking values in the integers with transition probabilities given by the probability that x at time L plus 1 is equal to k, given that x at time L is equal to n. This will be given by p n k, and this is for k in between 0 and n integer, and the sum from k equals 0 to n of p n k is equal to 1. Okay? So it's a non-increasing Markov chain. You cannot read because of the light? Okay. So it's a non-increasing Markov chain, homogeneous in time. Okay. And we will denote by xn L for L bigger or equal than 0, the Markov chain issued from x0 equal to n. Okay, so for all n integer positive, we denote xnl, the Markov chain started from n. Okay, and p n star, the log in 0, 1 of xn 1. So p n star dx is the sum of the weights p and k multiplied by the Dirac mass at k divided by n in dx. Okay, this is for x in 0, 1. Okay, so it's this atomic measure on 0, 1. Okay, and the theorem reads as follows. So assume there is a sequence an of the form n to the gamma L of n for n positive for some gamma strictly positive and L slowly varying. Okay, and a measure mu on 0, 1 such that an times 1 minus x times the measure Pn star dx converges weakly as n goes to infinity towards mu dx. Okay, so this convergence holds for every continuous unbounded function on 0, 1, okay, towards the integral of mu for the same function. Okay. So if we have that, then in that case, we have that the process yn t defined by xn, so that the Markov chain started from little n at time integer part of a n t divided by n as for t positive, okay, n positive, then the process or the sequence of processes the sequence of processes defined by this relation converges in the sense of Skorokhod towards a self-similar Markov process with non-increasing paths okay. Let's say this process is X. And furthermore, X can be represented, can be expressed as xt is equal to x0 times the exponential of minus sigma of tau s for s positive, where sigma is a subordinator so a Lévy process with non-decreasing paths okay, and tau of s is the infimum over u strictly positive, such that the integral between 0 and u of exponential of alpha sigma v minus dv is bigger than s, okay, and sigma has a Laplace exponent which is related to mu. Okay? I will not say the relation at the moment, but just check the theorem. So we have again a normalization of the process. Okay? So we have a Markov chain that can be normalized in this way. Okay? under this assumption of regular variation for this sequence and convergence of this measure, okay, we have that the limit exists in the sense of Skorokhod topology. Okay, the limit has a strong Markov property, okay, as it does for x, okay, and because x has non-increasing paths, the limit should also have non-increasing paths. Okay, so that's the first part. And then the second part is that xt can be obtained as the exponential of minus a subordinator at a random time. And this is something that is very, very important. Okay, so we are observing the same path of sigma, okay, but at a different rate. Okay, a rate that is dictated by this functional that is here. Okay. Well, this is a result that, for the first part, I will say is not surprising. It's just something similar to what we saw in Lamperti's theorem. You have a question?
What was alpha?
The alpha here is, gamma. Thank you. Thank you. Yeah. Is alpha somewhere else? No, just there. Okay. Yeah. Gamma is, the gamma there is the gamma here. Okay. So for the first part, this is not surprising. It's just another version of Lamperti theorem, okay, of scaling limits. And it's natural to have the Markov property because we have a Markov process at the beginning. Okay, but the representation is something that so far is surprising. Okay, because so far we haven't said anything about Lévy processes. Okay, but this fact, in fact, is not something that they observe in the theorem. I mean, it was not the first time that it appeared. It's something that was already known. It's something that Lamperti observed in the 70s. Okay, so Lamperti did a lot of contributions to the theory of self-similar processes. Okay, in particular, he established a connection between positive self-similar Markov processes and Lévy processes, from where this relation is coming. Okay, so what they did in the paper is to identify the limit, identify this sigma, okay, and identify the law of sigma. More precisely, to express the Laplace exponent of sigma in terms of mu. But I will make all these statements more precise. But what I wanted to notice here is this representation. Okay? That the limit process is the exponential of minus a subordinator time change. Okay? And this is the main motivation of this course. That there is a connection between, yeah. X0 equals to 1, yeah, in this construction, yeah. Yeah.
The process hits 0, then it stops?
Yes. Yeah. If the process hits 0, it stops, yeah. Because of the way we build the process, this process is absorbed at 0, okay? And the same happens for that one. Once it hits 0, it dies at 0. Yeah. And they actually prove a bit more. They prove that the lifetime of this process converges to the lifetime of this one. Yeah. So let's write maybe it's not very convenient to take x. Should be set maybe. Say C. Because x was for the Markov chain, isn't it? Yes, that's right. So this is equal to 1. Okay. So they also prove that if AN is the absorption time of x at 0, or at any other, or at any other point, okay, just the absorption time, okay, into one point, okay, then AN times AN converges as n goes to infinity in law towards the exponential functional of minus gamma sigma s ds. Okay? And this is the lifetime of exponential minus sigma tau s s positive. Okay. And they prove that the convergence holds not only in law, but also that the convergence of moments holds. AN to the power k, the expected value, converges as n goes to infinity to the expected value of this exponential functional to the k. Okay? Okay. So this is another limit theorem, now connecting and answering somehow your question, which is under which conditions we have the Markov property on the limit. Just something like that. Okay. The theorem of Bertoine and Korczewski reads something similar, just we have a more general convergence here. I didn't say here, I didn't say anything here because there is something missing here. Mu is a measure that is finite. A finite measure. Okay? The measure mu should be finite on 0, 1. Okay?
For the definition of AN,
Yes.
it is the absorption time of xn.
Oh, yes, yes, that's right. Yes. Yes, yes. Yes. Well, so the theorem that I stated before about the characterization of self-similar processes as scaling limits was one of the main contributions of Lamperti to the theory of self-similar processes, but that was not the main one. There were two other important contributions at least. The first of them is that what we call nowadays the first Lamperti transform, which states that if X is a self-similar process started from 0, then the process theta t defined by exponential minus, so let's say here that an alpha, what am I saying? 1 over alpha. Yeah, alpha self-similar process started from 0, then the process exponential minus alpha t x exponential of t as t is in minus infinity plus infinity is an stationary process. Okay? And any stationary process can be represented in this way. So that is why the work of Lamperti is also very popular in the community of stationary processes. Okay? And that is very easy to check, isn't it? It's just a straightforward consequence of the scaling property that this process is stationary. Okay? And the same if you take a stationary process, you invert this transformation, you easily check that the process has the scaling property. Okay? Okay. And the second transformation is the main motivation of this course. Okay, and this one establishes a bijection between self-similar processes that are positive and Lévy processes. I will state that clearly. I will state a theorem. Okay, and let me just mention that there is a third transformation that obtained Lamperti. Which is that, but is not related to self-similar processes. Third, okay, is that there is a bijection between continuous state branching processes and spectrally positive Lévy processes. That is, processes with no negative jumps. Okay? These two bijections are given again via time change. Okay? I will not establish this one. I will not describe this one, but I will describe this one, which is our main motivation. Okay. So again, Lamperti is very popular in the theory of continuous state branching processes. Okay. And then he retired. So let me write the second Lamperti transform. I will just call it all the time Lamperti transform because I will not be speaking about the two other transformations. Okay? But it reads as follows. He obtained this in a paper just before he retired in the 72s. In the 72. It reads as follows. So let x little x for x in R be a family of R valued one over alpha self-similar Markov processes and let T0 to be the first time where x becomes negative. Well, this depends on the starting point. Or okay. So just the first passage time below 0 for x. Okay. And we consider the process killed at 0. Okay, so let x tilde x t indicator t is smaller than t0 for t positive be the process killed at t0. Okay. So when the process goes below 0, we will leave it at 0. We will take 0 as a symmetry state. Okay? So 0 is a symmetry state. Okay? Do we have more white chalk? It looks blue. Okay. So it reads as follows. So we have that xt x killed at 0 can be written as xt x indicator t is smaller than t0 is equal to x times the exponential of psi at time tau t x to the minus alpha times the indicator that t is smaller than x to the alpha a infinity, and this holds for all t and all x positive. Okay, where psi is a possibly killed Lévy process taking values in R and tau t is the inverse of the additive functional given by this expression. This for t is smaller than a infinity, which is the integral exponential alpha psi s ds. Okay. What is a possibly killed Lévy process? Is a Lévy process that can only live up to an exponential time. Yeah.
Where do you close the exponential?
Oh, I close it here.
Okay.
Yeah, so the indicator is for the exponential. Yes, thank you. Yeah, if not, it will be a stick to 1. You're right. Thank you. I will just remove the possibly killed because it's not very clear. So what do I mean by a killed Lévy process? It's just a Lévy process killed at an independent exponential time. Well, I didn't want to delete this, but it's just okay, just the coincidence of the main theorem of Lamperti and the theorem of Brownian of Hassan-Mirmont. So killed at an independent exponential time of parameter q bigger or equal than 0. Q equal to 0 means that the exponential is infinity, almost surely. Okay? So we observe the path of a Lévy process up to an exponential time, okay? And when that exponential time rings, we just stop the process and we send it to a symmetry state, okay? And we can identify the symmetry state in this case by taking it to be equal to minus infinity. Minus infinity. Okay? Just because the exponential of minus infinity is equal to 0. Okay. So there is something else. So we have that x can be written as exponential of a killed Lévy process, time change. Okay? And the process is killed. And now I will let you know when this is killed. Okay, so we will have that psi has an infinite lifetime. So q equals 0. And the limb sup of psi t as t goes to infinity will be equal to infinity, or more surely, okay, if the process is starting from x never hits 0, yeah, for all x positive, for all x positive, okay. So if we don't hit 0, if the process x does not go below 0, okay, we observe the whole path of the process psi, okay. C2 is the lifetime of psi is infinite, almost surely, so again Q equals 0, and the limit as t goes to infinity of psi t is equal to minus infinity, almost surely, if now the process hits 0 in a finite time and it hits 0 continuously. Okay. And the third condition is Q is strictly positive, so the lifetime is finite almost surely. Okay? Almost surely. And this happens if the process hits 0 in a finite time, but it does it by a jump. Okay. And these are all the possibilities. There are no other possibilities. Why there are no other possibilities? Because by the scaling property, it's very easy to check that if any of the conditions C1, C2, or C3 is satisfied for some x, then it is satisfied for all x. Okay? Well, this is essentially the end of the theorem. But let me just say, so why there are no other possibilities is because if the conditions are satisfied for some x, then they are satisfied for all x positive. Okay? And furthermore, with these three behaviors of psi, we have included all the possible behaviors of a Lévy process. Okay? For Lévy process, we can only have 4 behaviors, let's say. One is that Q is strictly positive, so the lifetime is finite. The second is that, or the 3 others are that Q is equal to 0, and the process drifts to minus infinity. Okay? Or it oscillates, or it goes to plus infinity. Yeah? And this, the case where the process goes to plus infinity or oscillates is covered in this setting. Yeah?
In C1, you write limits in superior?
Limit superior, yeah. The lim sup.
Limit superior.
Yeah. Should I write it like that?
Okay.
Yeah? Yeah. Mm-hmm. There's a limit superior, yeah. Yeah. So when Q is equal to 0, these two settings cover all the behaviors of psi.
Not limit, but limit.
The limit, the true limit. Yeah.
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 Okay.
So for a Lévy process, we have 3 possibilities when it has an infinite lifetime. So either it goes to minus infinity, or it oscillates, or it goes to plus infinity. There are no other options, okay? So this is one when it goes to minus infinity, and the two other are here, okay? And the other possibility is that the lifetime is finite, okay? Which is this one. Okay. And by construction, yeah, so by construction, look, we are taking the same path of psi, okay, but up to some time, okay? And if we kill the path of the process will go to the cemetery state by a jump, okay? So that is why here the process is jumping to 0, okay? Yeah, so in this case, this case here, we observe the whole path, and the path is going to minus infinity. Okay, the time change will not change that that behavior. Okay, it will just change the rate at which we approach to minus infinity, but we will approach to minus infinity continuously. Okay, so the exponential here will go to 0 continuously. Okay, that is what is happening here. Okay, so in all the cases, for every path, you will approach to 0 continuously. In the exponential of minus I will go to 0 continuously. Okay? And for the other case, we will never hit 0. Okay. Why we will never hit 0? Because remember that psi t, okay, psi t grows linearly, or at least linearly. Psi grows at least linearly, okay? Because of the law of large numbers for Lévy processes, okay? So that will make that if the lim sup of psi t as t goes to infinity is equal to infinity almost surely, then the integral will be equal to infinity almost surely. Okay? And why this integral is relevant? Why? Because this integral that is here is the lifetime of this process. Okay? x alpha times a infinity is the lifetime of x by the expression that we have here. When we are above this level, okay, this inversion that is here is not well defined. It goes to plus infinity because there is no value s for which we are above that level. Okay? So if there is a t such that t is bigger than x alpha a infinity, then the set s strictly of the s strictly positive for which the integral between 0 and s exponential alpha psi u du is bigger than t times x alpha, okay, is empty. Okay, so that makes that tau of t is equal to infinity for that t. Okay, then the exponential, the exponential of psi tau t will be equal to 0, okay? Because psi has been taken as minus infinity, okay? As the cemetery state, and the exponential of the cemetery state is 0, okay? So that is why this is the lifetime of x, okay? So in this setting, the lifetime is infinity almost surely, okay? So we never hit 0, yeah? So in the C2 and C3 cases, the lifetime is finite almost surely, and in the C1 case it is infinite almost surely. Okay? Is that clear? Is that okay? Okay. So this guy is the lifetime. Okay. In the C1 case, because the process is going to plus infinity in some eventually, okay, this exponential functional can only be infinite. Okay? So the lifetime will be infinite. In the two other cases, because the path of psi grows at least linearly or is only observed in a finite interval of time, the lifetime is finite almost surely. Okay? So in this case, when Q is strictly positive, we just observe the path up to an exponential time. So the integral up to that exponential time has to be finite. Okay?
So you must say that the lifetime of x is finite.
The lifetime of x, x, for all x.
Yeah. Upper blackboard, you say C has that beauty that.
Yes, it's confusing. You're right. Yes, that's right. That's right. Yeah, here we have to make clear that this for x. Yeah. Yeah, that's right. Yeah. Thank you. Thank you very much, Kui. Is that okay? Okay. How much time do I have left? So we start at 40:45. We should finish at 4? 4:15. Okay, so I still have half an hour. Okay. 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 Let me tell you how this time change behaves or transforms the path. Okay, so imagine you have the path of psi. Okay, so it will move, there will be some jumps. Okay. And then you have the exponential functional. Okay. So assume alpha is strictly positive. Okay. Then with this integral, we will observe when we are close to 0, we have something. This exponential is close to 1, so essentially it grows linearly. Okay? Then it becomes a bit bigger, the path. Okay, so the exponential functional grows a bit faster. Okay, and then, well, so let's say, yeah, it grows essentially linearly, and then it grows a bit faster. Okay, and then it goes negative. Okay, so the exponential becomes smaller. Okay, smaller than 1. Okay, so the slope of this exponential, the exponential still grows, the functional still grows, but grows as at a lower rate. So the slope is smaller. Then again we are close to 0, so it goes faster. Again it becomes bigger, so it becomes even faster. Okay, so this is how the path of A would look. Okay, but what is tau? Tau is the inverse of A. Okay, so this x is defined in terms of the inverse of A. Yes? Okay. So what is gonna happen when we take the inverse of this? The inverse will grow linearly when we are close to 0. Okay? And then it will grow very fast in these slopes when we are close to 0, and very slow when we are far from 0. Okay? So tau t will be something like linear, then it grows in here, it will grow something like that, and then here it will do something very fast. Okay, then again it will do something like that, and then again slow. Okay, so this is how tau t looks like. Okay, so observe that here we have the time scale of the inverse. Okay, but observe that this interval of time, okay, will carry all this path. Okay? So in the exponential, okay, we will see this path, but it squeeze into this interval. Okay? So it will squeeze here. Okay? And this one, okay, it will be stretched in here. Okay, so what we saw there, so just to make this slightly more dramatic, so imagine this is just something like looks like that. Okay, so here you will have something that looks a bit bigger. Okay, compared to this one here. Okay, yeah, and when we are close to 0, we will leave the path essentially the same. Yeah? Okay, so it changes the rate at which we travel along the path. Okay? But the path is essentially the same. We just play with it. Okay? We are not changing the jumps, essentially. We're just taking the exponential of the jumps. Okay? We're just taking the exponential of the continuous part. Okay? Is that clear? Yeah? I mean, I think that is kind of very important because if not, it's quite ambiguous, this transformation.
You understand what is a triangle thing is?
Well, yeah. It's just, I mean, imagine it's the same thing. It's just. I just wanted to explain that this bit that is here, with respect to this one, okay, it becomes very small, okay, and in fact this one, it becomes bigger. My drawing is not best because I did it the other way around, but yeah. Okay. Okay. What I would like to do in the rest of the course is to prove this theorem. The proof is not very difficult, in principle. And then try to get some properties from psi, transfer into properties of x, okay, and vice versa. From some properties of x, say in some cases something about psi. Okay? That could be easy, but in fact it's not easy because the time change is not is a random time change, and it's not straightforward to translate the properties from psi into the properties of x. Okay? Okay. There is an example that is well known and is studied in almost any course on stochastic processes, on stochastic calculus, which is the case of a Bessel process. Or a squared Bessel process. So this is the example of a Brownian motion killed at 0 and squared Bessel processes. Okay. So in this setting, we are going to consider a Brownian motion and we will take psi t, which is 2 times a Brownian motion plus 2 times c times t for t positive, okay, and we will take x to be the x is the one self-similar Markov process obtained via Lamperti's transform. So x t of x is given by x times the exponential of psi tau t divided by x, where tau of s is the infimum of t bigger than 0 of the integral between 0 and t of exponential psi u du bigger than s. Okay? And x here is positive, t is positive. Okay? So here we assume also that psi has an infinite lifetime. So q is equal to 0. Okay? So there is no killing time for psi. Okay. Here x has continuous paths. Okay. And it can be seen that x is solution to the stochastic differential equation, which is d xt is equal to twice the square root of xt with respect to a Brownian motion plus a delta dt. Okay, this for t positive, and yeah, and I will tell you what delta is. Delta is related to c. Okay. This is the SDE that defines a square Bessel process. Is everyone familiar with stochastic calculus? Is there anyone that hasn't followed a course on stochastic calculus? No? Okay. Okay. So to prove that, should I leave it as an exercise? Maybe. So, yeah, let's do it as an exercise. So, for that, apply Ito's formula for yt defined by x times exponential of 2 times bt plus ct. Okay. Yeah, that's okay. And use Dubin's Schwarz theorem for the martingale empty given by the integral from 0 to t of a square root of x of exponential bt plus ct as bs ds. Yeah. whose quadratic variation is x times the integral exponential twice bs plus cs ds. Okay? Okay, so you apply Ito's formula, okay? You will find that you can write yt in terms of an integral with respect to m, okay? But this is a martingale. This is with respect to b, okay? Yeah, with respect to the same b. So this martingale has this quadratic variation, okay? So the martingale taken at the inverse of the quadratic variation is a Brownian motion, okay? That will be beta, okay? The beta that we have there, okay? But in fact, this time change that you have here is also the time change that is appearing in the Lamperti transformation, okay? So with that, we'll reach this expression here. Yeah? Okay. There is something else. So I leave that as an exercise. And also, the exponential functional of exponential twice bs plus twice cs ds is finite almost surely if and only if C is strictly negative. Okay? C, so delta. So delta here, delta is equal to twice C plus 1. Okay? So if C is bigger or equal than 0, delta will be bigger or equal than 2. Okay? And in that case, x will not hit 0, okay, almost surely. And that coincides with what we know, because a square Bessel process of dimension bigger or equal than 2 never hits 0. Okay? And delta is the dimension of the square Bessel process. I didn't mention that. So delta is the dimension of the square Bessel process. Okay? And for dimension smaller than 2, that's equivalent to say that C is strictly smaller than 0. We know that a Bessel process, or a square Bessel process, will hit 0 almost surely in a finite time. Okay? Before writing another example, let me say two more things about the theorem. The first is a remark, or something that I didn't say, is that in the theorem, one should read that every self-similar Markov process killed at 0 can be expressed like that, and psi is unique. And yeah, given psi, X is a self-similar Markov process. Okay, so if you have a self-similar Markov process, you will find a unique self-similar psi, so that the representation holds. Okay, so if you start with a psi, you will find a self-similar Markov process. And the other is a corollary, which reads as follows. So let XX be a positive self-similar Markov process so P ssMp that dies at 0, okay, at time t0. So t0 may be finite or infinite, okay, and define Ct as the integral between 0 and t of xs to the minus alpha ds. Okay, so here is 1 over alpha positive self-similar Markov process. Ct is this exponential, this functional here. So we take xs to the minus alpha. Sorry, the Blackboard has a memory. So it's xs minus alpha for t positive. And we take bt to be the inverse. Okay. So we have that under Px, so the law of x starting from x, the process psi t defined as the log of x at time bt divided by x0 for t smaller than ct0 minus, okay, so the integral of c up to time t0, so before, so see, this integral here is well defined before c goes to 0. If it goes to 0, this integral will blow. Okay, so this process is a Lévy process. It is the Lévy process associated to x. It's a Lévy process that starts from 0, whose law does not depend on x and the description C1 to C3 holds. Okay? Meaning that if x does not hit 0, okay, then psi has an infinite lifetime and its lim sup is equal to plus infinity, and so on. Okay? And the lifetime of psi is ct0 minus, okay, which is the integral from ct0 xs to the minus alpha ds. Okay? But this is the limit on the left. Yes. We just approach this as we grow to t0. It's the same, yes. Yes. Yeah. This is ct0, and this we know is an exponential of subparameter q, which does not depend on x. Okay. It's just writing the inverse of the transformation we had in Lamperti transformation. It's okay. Are there any questions or comments? I wanted to continue all night long. No, that's okay. Yeah. Okay. Well, if not, you can ask now, or we can discuss tomorrow. Thank you.